homework M3 Part B for Module 3. All right, in this, I want you to use MATLAB to do Laplace transform calculations. And the reason I want you to do this is because you don't get lost in the tedium of doing all the algebra from the Laplace transform if you just think of it as an operator that you can implement in MATLAB. All right, so we're going to walk through one example. I'm going to do problem 1 for you, and then you can repeat this process for problems 2 and 3. Okay, so let's get started. All right, so for problem number 1, you're supposed to look at this ordinary differential equation and come up with the transfer function. So I've already started this for you. When you have something in the live editor, there's a text component. That's what this part is. It's white. And this part you can see is a little bit grayer. There's a little faint box around it. This is where you insert the code. All right, so we talked about in another video how I can, by inspection, write down the transfer function for this differential equation. So I take a look at that, and everywhere I see a derivative, I put in an s. All right, so on the right-hand side of the equation where I have the x's, remember that goes in the numerator. So that'd be 2, because that's the coefficient in front of that derivative, and then times s, all right, plus 1. All right, so that takes care of the x, the input side of the equation. Remember, that goes in the numerator. In the denominator, I have the second derivative of y, so that'd be s squared. And then plus 5 dy dt, so I'd represent that with just a 5 times y, 5 times s. And then finally 6y, and that would give me just the final 6. All right, so I can enter that, and when I hit run, if I don't hit a semicolon out to the right, you see the transfer function listed in kind of a nice looking format. Oh, and by the way, in case you're interested, you can right click on that and copy that as a LaTeX formula, which is really pretty clever. Okay, so next I want you to find the poles and the zeros of the system. All right, and so there's a trick for this. I'm going to use num as a variable for the numerator, den as a variable for the denominator, and then there's a symbolic command called num den, okay, that will separate a rational function into the numerator part and the denominator part. Remember, a rational function is just a ratio of polynomials. Okay, so when I run that, you see, yeah, there's the numerator, there's the denominator. I've got those separated out. From there, I can calculate the poles and the zeros of the system. All right, so the zeros can be found by just solving. Set the numerator. This double equal sign means you're making an equation and you're going to solve for the variable s. All right, and so I'll do the same thing with p for pole. All right, so what we remember is the zeros are the roots of the numerator, the poles are the roots of the denominator. Okay, so I can run that, and I get the 0 location at -1/2, and the pole locations at -2 and -3. All right, so we're trying to, learn how to interpret these things that we're seeing with the Laplace transform. Okay, so we now know the zeros and the poles. At this point, I can determine and graph the impulse response. All right, so H is the impulse response, and if you remember, it's the inverse Laplace, so I put an I in front of Laplace to get the inverse. The inverse Laplace transform of H. And when I hit run, that gives me an expression for the impulse response. Okay, I also wanted you to determine the partial fraction of H and mentally take note how the poles and the zeros match to the various components in the time domain solution. Okay, so let's do that. Here's what I mean. I want to do the partial fraction expansion like you did in your DFEQ class and maybe your dynamic systems, but we're not going to have to do any of the work. We're going to let the symbolic toolbox do the work for us. And I'm going to rename this because I want to save that H. So I'm going to call this HP. All right, so it's still the transfer function h but put in partial fraction form. So when I run that, I get HP is 5 over s plus 3 minus 3 over s plus 2. All right, so compare this to the original transfer function. I could have factored that into factors. I know what the poles are. So this would have been on the bottom s plus 2 times s plus 3 for the denominator. Okay, and so I can match this. I know that from the Laplace transform tables, 1 over or something over s plus 3 corresponds to the e to the minus 3t term. So this pole at minus 3 matches this component. And then the s plus 2 in the denominator here gives me the pole at minus 2 that matches this component. All right, so that's what I'm wanting you to get, is this correspondence between poles and terms of a response. Okay, so there we go. Next, we're using the ideas from convolution, system input, system output. We can now look at a unit step, and so I could call that x equal 1. Remember, that's a unit step. And then I wanted to show you, if I do this, this is, I think, going to throw an error. Okay, yes, it's confused about what are you wanting as the arguments for this Laplace, because normally the time function has a t variable in it. All right, so we're going to give it a hint, to use regular Laplace variables. I'm not sure why it needs that, but I wanted to show you that in case you get stuck. All right, so here we are. Lowercase x, the time domain, is equal to 1. Capital X, the Laplace transform, is 1 over s. Okay, so no surprise there. All right, but we want the step response, and so what we remember is that capital Y, the output of the system, is going to be x times h. All right, so when I run that, I get this new rational function. Okay, and so I can envision what's going to happen. I'm going to do a partial fraction expansion. It's now going to have 3 terms. It's going to have a term for s plus 2, a term for s plus 3, and this extra unit step term that is introduced from the input signal. Okay. Up in here, I said to graph the impulse response. I forgot to do that. So there's a real quick way of plotting symbolic functions. You just say f plot, and you give it the range that you want to plot over, the time range that you want to plot over. So let's go 0 to 6, just to take a look. Okay, so there's the picture that you would get for the impulse response. Okay, all right, so moving forward, capital Y is equal to inverse Laplace of cap Y, and I can also plot that. And we try to learn something every time we do one of these analyses. Okay, so what I see here from the plot is, let's see if I can move this window around. I can't get it to scroll. Darn. Okay, so what I see here is here's the step response, and indeed I see the 3 terms. I have the constant term. I didn't show the partial fraction expansion, but we could do that. Add that in. I'm going to, just so I can fit everything on the screen, I'm going to delete or comment out this plot. Okay, all right. So now here we go. We've got the partial fraction of y, all right? So that looks like this, and so I can see this e to the minus 2t term corresponding here, e to the minus 3 term here, and then this 1 over s has the 1 over 6. Remember, 1 over s is an inverse Laplace transform of 1, so 1 over 6 times 1. Okay? And we see our response. And so this system zoomed up, and then it leveled out at the value of the forcing function, right? Remember from differential equations, you talk about forcing functions. In this case, the unit step was the forcing function, okay? And this leveled out at that particular value that's, 1/6, but it has the same form as the forcing function, that being of a constant, okay? All right, well, let's move on down. Let's do the next one. We can let x be cosine of 4 times t. We calculate the Laplace transform. We look at h times x. We look at partial fraction. And we can calculate the time domain response. And plot that. All right, so we run this and we get some new output, and let's see if I can separate that out. Yeah, here it's scrolling a little bit. It scrolls to the top. I forgot how to change the size of the window. Okay, here we are. Okay, so looking at the different components here, we had the input x. Okay, so here we go. Here's the Laplace transform of x. This gives us a new output response where we take the input, s over s squared plus 16, times y of that times h of s, okay? And we can look at the various components. This one's a little bit trickier here because notice it took the partial fraction expansion and it put it as a linear component. It's just got a single power of s plus a constant divided by a quadratic component. A component that has an s squared in it, okay? This will always break up into a cosine and a sine, all right? So using Laplace transform tables, you could undo that and figure out exactly what part is the cosine and what part is the sine. So these two components match this partial fraction term, okay? Again, I think you did this in ODE. All right, and then here's the system response from the original differential equation. It's got these natural components that show up at either minus 2t and either minus 3t. Okay, so looking at the output, this is interesting. Remember, we hit it with a forcing function of a cosine. So it's going to take us a cosine or a sinusoidal. We don't know exactly what that phase shift would be, but it's a sinusoidal component that shows up at the output. You can see a little bit of a transient response where, it's not quite all the way up to a cosine yet, but eventually the e to the minus 2t term dies out and the e to the minus 3t term dies out, and you just get this sinusoid term that's left, okay? We didn't do the poles and zeros on this part, but I would like you to. Well, no, that's okay. I just want you to do the poles and zeros of the system, not of the signals, right? Okay, so that walks you through what I'm expecting to see. And what I'd like you to do is go ahead and do the same set of commands, looking at the same things for two different systems, okay? In one of the cases, I asked you to calculate the zeros, and the system doesn't actually have any zeros, right? If there's no place where the roots are equal to 0, like if you have a constant term, there's not going to be any, we call that, there's no finite zeros in that system. So that happens on problem 3. I just wanted to warn you about that, okay? But that's what I have for you for the homework. I'd like you to walk through that, and it's not just a matter of typing in the commands. You really need to think about, associating each part with the pole locations and trying to get some intuition about what you're expecting to see for the results. Oh my gosh, I am late.